I'm going to show you how to analyze a Bluetooth system that we have already made from beginning to end. We're first going to add the EE101 debug firmware into the project. We add an EE101.c file, and we also add an EE101.h file into our existing firmware project. In this case, we're using a PSoC 5LP microprocessor. And so once you have those files created in your project, you need to go to our website, EE101.com, click on the user's manual, go to the embedded firmware source code, and on this web page are the two source files that you need to copy into your project. Copy the EE101.c source code, paste it into your project, then go get the EE101.h contents, and paste that into your project. The EE101.h file then allows you to access all of the routines that are necessary in order to output the debug data from your project. First, we're going to build it to make sure there's no errors, which comes up error-free. Then we go into our main program, and in order to add the EE101 debug output, we first include the EE101.h file. Now we have access to all of the routines in order to output the data to our project. We will be adding output data into our main routine and our application, but first we need to go and define the I/O pins that will interface to our hardware. So in our hardware project, we're going to add two pins, debug 51 and debug 50. We're going to use the 2-wire EE101 debug interface. And we go back into the EE101.c file, and we start modifying it for our pins. We're going to leave the debug on. Change 1, you need to include any project header files that reference the I/O pins. Then you can change whether or not you want to use the debug interrupt. In this case, we're going to pick the 2-wire interface. 1 wire uses a UART and 2-wire uses 2 general purpose I/O pins. Here is where we define which I/O pins we're going to use in our project. These are some configurations, defaults for various processors. In this case, we're going to use the pin that we defined, debug 50, and we need to change these lines to set the clock high, to set the clock low, set the data line high, data line low, and also toggle the data pin. Now it doesn't matter which I/O pin is clock and which one is data, so you can choose either one for either. It auto senses the polarity. You just need to make sure that these lines will set that pin high or set that pin low. If you're using 1-wire mode, you need to define the routine that's called to output a byte onto that port. There's no other changes necessary, so we're going to build the project. Okay, now we have the interface to the physical pins. So we can now go back into our main and using the defines that are in the EE101.h file, we can go into our project in any location and add debug output. First one we're going to do is a hello world output. We're going to output some text on channel 0. I'm just going to basically say we got here. Now you can go through any of your other code and enter any other text output. We're actually going to go into one of our loops. This is the main loop of this particular application. And on channel 1, we're going to just output the fact that we are at the top of the loop. We're just going to build and program our device. Now it's programming the PSOC. Which, by the way, is a Bluetooth enabled module from Cypress. And we basically go to the EE101 controller and we press start, or capture, excuse me. You'll see now we're outputting the while ones that are the main loop that we have, and you can see that loop time of that routine is 259 microseconds. So now we're going to get a little more intricate. This is a Bluetooth device. We have a portion of code that is run when the device is connected to something, and there's another mode in which it is advertising in order to get connected. So we're going to output two debug outputs, one that says it's connected and one says that it's advertising. This allows us to see the actual state of this program. Again, you build and program your device. It's now downloading the device. It will run. Now when we press start, you will see that it's not only outputting the while one, but on a different channel, it's outputting the BLE advertising or connected state. So we're now going to go in, we're going to connect this, but there is a timeout timer that allows it to go to sleep. Our main goal is to characterize the current during this sleep mode and to analyze whether or not the sleep is happening correctly. So we're going to output this last hit timer, and the value label will change on the screen to last hit timer. You will see when we connect, the timer will start, and after 5 seconds, the device should go to sleep if it was not, if the timer expires. So when we press capture, you can see that it's advertising. The last hit timer line is showing the value of the timer. We are now going to connect to this device to our cell phone, and you'll notice that the last hit timer starts counting. As soon as it gets to 5, you will see that it outputs a text string that says that it's sleeping. Okay, so we can see that once connected, if the timeout last hit timer expires, that yes, indeed, it does go to sleep. If we search from the beginning to the first connected, we'll put a marker X1 on the connected event. You can see it right there. It changes from BLE advertising to BLE connected. And you can see that that is when the timer, last hit timer, starts counting. So what we really want to do is we want to measure the current during all this. So we pull up the the analog channel settings, and we're going to use this resistor in the supply line. We put a 10.4 ohm resistor in the supply line. You press save and you simply press capture. We're going to reset our device right now, and you'll see that the debug data is outputting. You see the analog channel 1 is showing the actual current that is being consumed. We just connected the device. Our timeout timer is counting, and as soon as it expires, it goes to sleep. And now you can see the characteristic of all the current of the system. You see the current at startup. You can see the advertising pulses on the Bluetooth. In this case, it's advertising at 27.5 millisecond intervals. Those are the 3-channel bursts of the Bluetooth advertising traffic. Sort of idle current in this case is about 8 milliamps. The transmit current is about 20 something, 22. Somewhere along the line, it connects. You can actually see the LED blinking in the current. And here you see it transition from advertising mode to connected mode. This device advertises on 3 channels. As you can see, the three bursts. And once it's connected, you can see it's doing single transactions at 30 milliseconds intervals. When it finally expires, you can see that once it goes to sleep, this particular device drops from 8.3 milliseconds to about 159 microamps going into sleep mode.